Jai Hind everyone. Today I am going to talk about the state space analysis, and particularly these are the contents from the state space analysis in today's lecture that I am going to cover. That is the state transition matrix, what are the properties of the state transition matrix, and then another topic controllability and observability, and following the examples, followed by the examples. Okay, so what is the state transition matrix? First topic is the state transition matrix. So state transition matrix can be defined as a matrix which satisfy linear homogeneous state equation. See, first of all we have the state equations with us, that is axt x dot is equals to axt plus but, right, and output equation is yt is equals to cxt plus d of ut, right. If this is the output equation and this is the state equation, this is xt, x dot t, and this is yt. Okay, now if input is 0, then ut will become 0 in both the cases, and particularly let me talk about this equation, about this state equation. Here we are having two components, axt and but, right. So this is axt is the homogeneous part of the equation, state equation, and but is the forcing function, right. If input is 0, that means ut is equals to 0, then we are left with x dot t is equals to at, a into xt, which is the homogeneous part of the state equation. So the state transition matrix is a matrix that will satisfy the linear homogeneous state equation. Now taking Laplace of the Laplace of this above equation, we will get s into xs minus x0, right, is equals to a into x of s. Okay, now if since s is an operator and a is a matrix, so I'll multiply this s by the identity matrix, which is of the same order as of the a matrix, right, this a matrix. Okay, so si minus a into xs is equals to x0, where x0 is the initial state of the system, and so xs can be written as si minus a inverse into x0, right, where this si minus a is said to be the non-singular matrix, right, sorry, singular matrix. Now taking inverse Laplace transform of above equation, we get xt is equals to Laplace inverse of si minus a inverse into x0, right. Now we also know that phi t xs is also equals to phi t into x0, right. If phi t is an n cross n matrix and x0 is the initial condition, then this is the solution of homogeneous equation. And if we compare the equation number 1 and 2, we will get phi t is equals to, sorry, we will get phi t is equals to si minus a inverse into x0. Now if we compare, and similarly if we are taking Laplace inverse of phi t, right, which is coming out to be phi s, then it will be coming out of Laplace inverse of si minus a inverse into x0, right. Now if we compare these two equation number 2, right, if we compare the equation number 2 with the equation number 1, we are getting a phi t is equals to Laplace inverse of, sorry, this is phi s is equals to Laplace inverse of si minus a inverse, and from here this is phi s is equals to Laplace inverse of si minus a inverse, right, and this is, if after comparing, after comparing these two equation, x naught will get cancelled here and phi s will come out to be only Laplace inverse of Si minus A inverse. Just a moment, this is excess and this is also excess. If I am comparing these two, then okay, after taking Laplace inverse, so I can write this is, let me correct it, this is from the solution of homogeneous equation. From the solution of homogeneous equation, we have xt is equals to phi t into x0, right? Now if we compare this equation with this equation, these two equations, right, then phi t is coming out to be, or let me write this, xs is equals to phi s into x0, and if I am comparing this equation with this equation, then I am getting that phi t is equals to, phi s is equals to Laplace inverse of Si minus A inverse, phi t is equals to, and finally this, and finally phi t is Laplace inverse of Si minus A का inverse, ठीक है, and it also can, we can write it as e raised to the at, and this is the equation for the STM. Okay, so STM, what STM signifies? It is, STM signifies the transition of matrix at any time t is equals to 0 towards any state at any time t, ठीक है, where for t greater than equal to 0, right? Its name is representing its significance, state transition matrix, the transition of matrix from a initial state x0 to any state xt for t greater than equals to 0. Now the properties of STM are, phi 0 can be equals to e raised to the power a0. If you put t is equals to 0, then it comes out to be an identity matrix, right? And phi t is equals to et if e raised to power at, phi of minus t ka inverse will be equal to phi of minus t, right? And if we add 2 times, then phi t plus t1 plus t2, then it comes out to be e raised to the power a t1 plus t2, or you can also write it as e raised to the power a into t1 into e raised to the power a into t2. In terms of phi, you can give the multiplication of the 2 phi t1 into phi t2, and if phi t raised to the power n will can be written as phi into nt, right? And it can be written in terms of e raised to the power at into nt. You can also write it as e raised to the power n into a into t, right? And another property is phi t2 minus t1 into phi t1 minus t0, then you can directly write it as phi t2 minus phi minus t0. Okay, so now this is the example here. Consider this system where xt is equals to, x dot t is equals to minus 3 1 minus 2 0 xt 0 and ut into yt is equals to 1 0 xt. So we have to find out the state transition matrix for this system. So first of all, we'll compare this equation with the standard state equation, then we'll get the value of a from here, which is equals to minus 3 1 minus 2 and 0. And since we know that phi t is equals to Laplace inverse of Si minus A ka inverse, right? This is our STM, e raised to the power at will be equals to Laplace inverse of Si minus A inverse. So first of all, I will find out the Si minus A. Okay, so Si minus A will be operator S, 1 0 0 1 is the identity matrix, minus A will be minus 3 1 minus 2 into 0. So it is coming out to be S plus 3, okay, and this is minus 1 and this is 2 and this is S. Now taking determinant of Si minus A, so determinant will be s into s plus 3 minus of minus 2. So it is coming out s square plus 3s plus 2. Okay. So if I am taking factors, then it will come out to be s plus 1 and s plus 2. Okay, यही आएगा ना, s square plus 2 और plus 3s, हाँ यही आएगा, right? Now what is, we have to find the adjoint of si minus a for the inverse, right? So do I have another slide for this? No. Okay. So for this, now adjoint of, let me finish it up here. So the adjoint of si minus a will be equal to, first of all, let me find out the cofactor of si minus a. C11 cofactor of si minus 1 will be s. C12 will be equal to minus of minus 2. C21 will be equal to minus of minus 1, that means plus 1, and C22 will be equal to s plus 3, right? Now si minus a inverse अगर हमें find out करना है, then the formula will be adjoint upon determinant of si minus a. Now adjoint will be s minus 2 and this is 1 s plus 3, इसका transpose upon determinant is s plus 1 और ये आएगा s plus 2, ठीक है? So this is si minus a का inverse, ठीक है? Now इसको clear कर दें, let me use another pen so that there will be no confusion. Now we can directly write the si minus a का inverse अगर हम लिखें और उसका भी लाप्लास इन्वर्स हम लें तो हमारे पास क्या आएगा यहाँ पर, s अपॉन s plus 1 into s plus 2 का लाप्लास इन्वर्स, this will be the term, ठीक है? Then इधर 1 अपॉन s plus 1 into s plus 2 का लाप्लास इन्वर्स, ठीक है? And third term will be Laplace inverse of minus 2 upon s plus 1 into s plus 2. Okay. And the fourth term will be s plus 3 upon s plus 1 into s plus 2. ठीक है, ये हो गई हमारी पूरी मैट्रिक्स. When I am taking Laplace inverse of all these individual terms, then answer will be this. Okay, how you will take the Laplace inverse? By taking the partial fraction and then putting the value of the constants and taking the inverse Laplace. The value will be, this will be the value for the phi t. Okay. So आपको करना कुछ नहीं है. First of all, you have to find out the value of a, then just put it in the formula Laplace inverse of si minus a inverse and you will get the value of phi t. So next topic is the controllability. So a system is said to be controllable if the initial state of a control system are transferred, or you can say changed to any other desired state by a controlled input, but in a finite duration of time. So this controllability and the observability are determined by using the Kalman test, as these are introduced by the Kalmans in 1960, right? And for any CISO system, that means single input and single output system, the controllability matrix can be it is represented by QC, and it can be represented by the formula b into a square b up to a n minus k 1 into b. Here these are the, so basically this controllability is dependent upon the two matrices, that is a and the b, right? Here this matrix QC is basically of the order of n cross n, right? So if the determinant of QC is non-singular, then only, non-zero, then only the system is said to be controllable. Okay. So basically you have to follow this formula only. Now let's do one example on this formula. So this is the system is given to us and we have to find out the controllability of the system. So here from here you can see this is x dot is equals to ax. So this is matrix A plus bu. This is matrix B is equals to y into cx. This is matrix C and this is matrix D, which is equals to 0 here, right? Since the matrix A is of the order of 3 cross 3, right? So we have to find out the value of QC till 3 terms, n minus 1, that is 3 minus 1 is 2, okay? So the formula will be B into AB into A square B, okay? We have the term B here 0 0 1, I can directly write. Now AB will be equal to multiply A with B, I am solving here. For A into B, this will be equals to 0 1 0 0 0 1 minus A naught minus A1 minus A2 into B will be 0 0 1. So it is 3 by 3 and it is 3 by 1. So another matrix that I am getting here after solving this will be 3 cross 1, okay? So you can multiply this and we are having 0 here. When we are multiplying this row with this column, we are getting 1 and by this only we are getting minus A2, okay? So value of AB will be here this. Now similarly you can find out the value of A square B. For that, first of all you have to find out the A square, okay? 0 1 0 and 0 0 1 minus A naught minus A1 and minus A2 into 0 1 0 0 0 1 minus A naught minus A1 minus A2 into B. So after solving this value, you will get 1 minus A2 and A2 square minus A1. Okay. Putting all these value in this formula, you will get this. Okay. First of all B, then AB that I have shown here, and A square B. After calculating, you will get this value 1 minus A2 and A2 square minus A1. Now we have to find out the determinant of this term. So what I am doing here is I am going to find out the determinant of, this is QC here. So this determinant will be 0 into something is 0 only, okay, and minus the gain 0 into something is 0 only, and now last term is 1 into, so this is the term, then it comes out to be 0 minus 1, okay, 0 with this 1 minus 0. So it is basically coming out to be 1. So determinant of QC here is equal to 1, which is not equals to 0. Since the determinant is non-zero, so this system is controllable, absolutely controllable in nature, okay. So what we have to do, we have to just apply the formula depending upon the rank of A, and we have to just find out the determinant of this control matrix, and if it is non-zero, then the system is controllable, and if it is 0, the system is non-controllable in nature. Now coming towards the observability. So a control system is said to be observable if it is able to determine the initial states of the control system by observing the outputs, but in a finite duration of time. Again, this observability will be checked by using the Kalman's test, as it was introduced by Kalman's in 1960s, and this controllability is dependent upon matrix A and B. Similarly, the observability is dependent upon the matrix C and A, right? So this is the formula for the controllability observability matrix, that CT transpose of matrix C into A into T into CT, then AT square into CT up to so on till A transpose up to n minus 1 and into CT, right? So here again this matrix Q naught, that is observability matrix, will be having the rank order n cross n, right? And n is the rank of the matrix A, okay, and if it is again not determinant of matrix Q naught is not equals to 0, then the system is said to be observable, otherwise the system will be non-observable. So let's again solve another example on the observability. So we have this system again where x dot is equals to ax plus bu. So if you compare this given system with the standard state equation, which is x dot is equals to ax plus bu and y is equals to cx plus du, then you will get the value of matrix A, B, C and D. So from here, this is the matrix A, this is the matrix B and this is the matrix C, right? So we have to find out the value of Q naught, which will be equals to here C transpose into C transpose into A transpose C transpose and AT transpose ka square into C transpose. Okay, as this is of order 3. So from here we have n minus 1, that means AT square into CT. So C transpose, this is C, so C transpose will be 1 0 0, right? Now A into CT can be calculated as AT into CT, right? Can be calculated as here. Now I am directly writing the transpose of matrix A. This is 0 0 1 and this is minus A naught minus A1 and minus A2 into CT will be 1 0 1 0 0. So this is of order 3 cross 3 and this is 3 cross 1, right? Okay, so it is again coming out to be another matrix which is of the order of 3 cross 1. So when I am multiplying this, I am getting 0. When I am multiplying this quantity, this with this, okay, then here I am getting 1 and I am multiplying this quantity with this, again I am getting 0. Okay, now another is AT, you have to calculate the square of T transpose ka square and then multiply it with CT, right? So you will be getting the value which is coming out to be 0 0 1. Okay. So let me write down, and you have to calculate this. Due to short of time, I will not going to calculate this. I am having the value directly with me, which is coming out to be 0 0 1. It's a column matrix again. Okay, 1 0 minus A1 and 0 1 minus of A2, and then you have to multiply it 1 0 0 1, and out of it you will get the answer which is coming out to be 0 0 1. Now when you put all these value in this equation, you will be getting this matrix, right? Now you have to find out the determinant of matrix Q naught, right? So determinant of matrix Q naught will come out to be 1 into 1 minus 0, right? Again 0 into something, it comes out to be 0, plus 0 into something, it comes out to be 0. So finally I am getting the determinant of matrix Q naught, which is equals to 1, that is, it is not equals to 0. So this system is called as the observable, as it is having non-zero determinant, right? Now solving for another example, the last example, we have been given the system x dot is equals to, this will be Ax, this will be Bu and this will be C. Now we have to find out whether the system is controllable or not, whether the system is observable or not. So from the definition, this is of matrix 2 is matrix A is of the order of 2 cross 2. So for controllability QC, we have to just find out B into AB. Okay, so B is this and AB will be A is 2 0 minus 1 and 1 and B will be 1 minus 1. So it has come 2 by 2 and this is 2 by 1. So it is coming out to be 2 by 1 ki matrix, which will be equals to this into this, that is 2, then this into, okay, 2 by 1 ki matrix hi aayegi, okay, this into this is 2 and this into this, that means minus 1 minus 1. So it is again minus 2. Okay, so it is 2 or minus 2 ki matrix aa rahi hai. Okay, so QC can be written as here B is 1 minus 1 and this is 2 minus 2, and if I am going to calculate the determinant of QC, then it is coming out to be minus 2 minus of minus 2, which is equals to 0 here. Since the determinant of QC is 0, so this system is not controllable, right? Now let's start with the let's go for the observability. Now for observability, you have to check the formula. Now for control observability, we have Q naught will be equal to C transpose and A transpose into C transpose, right? So C transpose here is 1 and minus 1. So C transpose will be come out 1 and minus 1. Now A transpose into C transpose will be 2 0 minus 1 1. This is 2 0 minus 1 1. I am directly writing the values here. Okay, so this is of 2 cross 2 and this is 1 cross 2 actually. Okay, how come? C transpose into A transpose hona chahiye. Okay, sorry. This is C transpose into A transpose. This also matter actually. 2 minus 1 0 and minus 1, right? So this is 2 by 2. So here I am getting the matrix of the order of 1 cross 2. That means this into this will come out to be 2 and this into this will again come out to be minus 1 and minus 1 is minus 2. So C transpose into A transpose will come out to be 2 into, let me write it, C transpose into A transpose, okay? It is coming out to be 2 into minus 2, right? Now let me put the values in the matrix Q naught. So C transpose will be 1 and minus 1, 1 and minus 1, and CT transpose into AT transpose is 2 and minus 2. Now if I am finding the determinant of Q naught, then it will be this into this is minus 2 and minus of this into this is again minus 2. So it is coming out to be 0. Since the determinant of Q naught is 0, that means the system is not observable in A. Okay. So that's all for today's lecture. Thank you so much.